Good morning, students. Myself, Vijay Shankar from ECE Department, Chipro Engineering College. Today, we are going to discuss about the very important topic, the boundary surfaces. The boundary conditions between two dielectrics and boundary conditions between the conductor and the dielectric. There is a two types. One is boundary conditions or the boundary surface between conductor and free space. Free space is nothing but the dielectric only. And another one is a boundary between conductor or the conductor, dielectric and the dielectric, means dielectric 1 and the dielectric 2. In this, you have to find out the tangential components and the normal component. Nothing but E tan and D tan. E tan means electrical and the electrical field and the electric field and the electric flux, E and the D. And similarly, you can find out the magnetic field and the magnetic flux, the tangential components, and the normal components for electric field and the magnetic field and electric flux and the magnetic flux. First of all, you can see the boundary conditions between the conductor and the free space. So the boundary conditions between conductor and free space. Means conductor is conductivity sigma, free space representing the epsilon. Okay. Here the boundary is between conductor and the free space. There is a boundary line we have. Below the boundary line, we can take the conductor, and above the boundary line, there is a free space, epsilon. Consider a boundary between conductor and the free space. The conductor is ideal, having a infinite conductivity. Means in the conductivity, in the conductor, conductivity is more. Conductivity is very high. In this free space, dielectric is very high. Such conductors are copper, silver, etc., having conductivity of order of 10 power 6, I think it is, and can be treated as ideal. For ideal conductor, it is known that the field intensity inside a conductor is 0. The field intensity means either D or E. E is equal to, and the D is equal to, both are, it is a zeros. The field intensity inside a conductor is a 0, and flux density inside a conductor is a 0. Nothing but E and D, electric field and the electric flux. No charge can exist within a conductor. The charge appears on the surface. The charge appears on the surface in the form of surface charge density, nothing but a rho s. There is no charge appears in the conductor, okay, within the conductor, but there is a charge appears on the surface. Suppose if I am taking the boundary like this, here the epsilon, the dielectric, and here the conductor is there. Inside there is no, the electric field is a 0, electric flux is a 0, and similarly rho s is also the 0. Where it is a rho s, we have the on the surface. The charge appears on the surface in the form of a surface charge density, nothing but the rho s. Okay, the charge density within the conductor is 0. Rho is equal to 0. Thus, rho v, let us take it as a rho v here. Thus, E bar, D bar, and rho v within the conductor is a 0. While on the surface means there is a surface charge density is there. While the rho s, the surface charge density on the surface of the conductor. But inside there is no any charge. Simply the volume, total volume is a 0. Electric field is a 0. Electric flux is a 0. And on the surface there is a rho s. To determine the boundary conditions, let us use the closed path of the Gaussian surface. in the figure, the C is a very, very important, my students. So listen carefully. A boundary line, if I am taking here, below the boundary there is a conductor. Below the boundary there is a conductor. It's a boundary line. So this is a total arc. Is a boundary. Above the boundary line, the free space, nothing but epsilon, dielectric, and conductor is a sigma or conductivity. In the conductor, there is no field. Electric field is 0. Electric flux is also the 0, and the charge is not there in the conductor. But on the surface there is a rho s. To find the tangential component, let us take is a rectangle here. A rectangle A, B, C, D, and A. Okay. The direction is also AB, BC, CD, and the DA. Observe here, A and B, A, B is in the free space, C and D is in the conductor. Okay, means the integral of 1 to A or A to B and B to 2 is in the dielectric free space, this total area, and the 2 to C, C to D, and D to 1 is totally, it is on the conductor. Okay, to find the tangential component for the electric field, draw a tangential line E tan bar and a normal E normal. Okay, this is a line for the En bar and this is a line for the E tan bar. Okay, similarly to find the D tan bar and the Dn bar. To get it is a D bar, and here also to get the E bar. First of all, I am finding out the tangential component of electric and the electric flux. For that, we can assume here a rectangle A to B, B to C. In this, the B to C, B to the point 2, and the point 2 to the C also. So total height is a DH here, and C to D, the total width is a delta W, and the D to A, the height is delta H, but D to 1 is in the conductor and 1 to A is in the dielectric. Got it, my students? So diagram is very important here. And E bar at the boundary. Let E bar be the electric field intensity in the direction shown in the figure 5.11. Is the 5 point, let us take okay, I will explain. Making some angle of the boundary, this E bar is resolved in two components, the component tangential to the surface E tan and the component normal to the surface En. Is to know that the integral E bar dot DL bar is equal to 0. Integral E bar dot DL bar is equal to the 0. Using this relation, the integral E bar dot DL bar carried out a closed counter is 0. That is, work done in carrying unit positive charge along the closed path is 0. We know this is the equation we have. In this, consider a rectangular closed path. See, this is a boundary we have. I take that is a rectangle. A and the B with the width of delta omega, and the height is delta H, and on the boundary B to 2 and 2 to C and C to D, the width is delta omega, and D to A, again the height is delta H. From D to 1 is in the conductor, and 1 to A is on the dielectric. Epsilon and the conductivity. Here in the conductor, E bar and the D bar is both are the 0, and the rho V is also 0. Okay. Using this, the integral E bar dot DL bar, if I am taking the one integral A to B E bar dot DL bar, and another one is a B to C E bar dot DL bar, and C to D E bar dot DL bar, and D to A E bar dot DL bar is equal to 0. Got it, my students? Now, see the A to B and the C to D. A to B is in the dielectric and the C to D is in the conductor. What we are saying, the conductor E bar value is a 0. E bar value is a 0. The closed contour is placed in such a way that its sides AB and CD are parallel to the tangential direction to the surface, while other two are normal to the surface at the boundary. Okay. A to B and the D to C. The remaining whatever we have, the D and the BC is a normal components. Why? The tangential component is a E tan, is parallel to AB and BC, and E normal is parallel to the AD and BC. To get it is a E bar. Okay. Next, it is the rectangle is an elementary rectangle with elementary height the delta H and elementary width the delta omega. The rectangle is placed in such a way that half of it's in the conductor and remaining half is in the frequency. Or the frequency, sorry. Remaining half is in the free space. Thus, the total height of the B and C is a delta H, and B2. So see here, the B2 to the height is delta H by 2. Okay, my dear students. And the remaining 2 to D, 2 to C is also delta H by 2. And similarly, D to 1 also delta H by 2. And 1 to A is also delta H by 2. The half part is in the conductor and half part is in the dielectric. Okay. Now, the portion CD is in the conductor, E bar is equal to 0. The portion CD is in the conductor, E bar is equal to 0. So, A to B is there. And all the total 4 integrals, A to B, B to C, and C to D, totally the third integral what we have here, C to D, E bar dot DL bar is total in the conductor. So in the conductor, E bar is equal to 0. Okay. So third integral is a 0. As this integral you can modify A to B. The first one is A to B, E bar dot DL bar, and second integral B to C. So I am writing that B to E bar dot DL bar plus and 2 to C E bar dot DL bar. Okay, the total C to B divided as a 2 parts because B to T is in the dielectric and 2 to C is in the conductor plus the D to A. Already the C to D is 0. D to A. Again the D to A I am divide that the D to 1 E bar dot DL bar plus 1 to A E bar dot dl bar. Total integral is a 0. Now see here also which integral is in the conductor and which integral is in the dielectric. So B22 is in dielectric and 2 to C is in the conductor. 2 to C, whatever it is, a 2 to C integral becomes a 0. And D21 is in the conductor, so D21 is also the 0 because in the conductor E bar is a 0 value. And 1 to A is in the dielectrics. So finally again this integral is changes as integral A to B plus integral B to 2 and integral 1 to A. What is the integral A to B? The total width is a delta omega. Okay, nothing but E bar into something and DL bar delta omega into the direction. So total we get the magnitude only. That magnitude is E bar into the integral of AB to the DL bar. You can write as a width. E bar into delta omega as a first integral. This first integral is equal to E bar delta omega. Okay, and that E bar here as a tangential component because we are finding out the tangential direction. E tan into delta omega. E bar is nothing but E tan delta omega. The total integral A to B DL bar is equal. Okay. So next, second integral saying that B to C, E bar into B to C DL bar, En into, because in the parallel direction is a tangential component, and the C to B, AB, C, D, A to B is a delta, and B to C is a tangent parallel to that of the normal component. So take the E bar is an En, B to C the DL bar, but B to C, B to 2 is in the free space and 2 to C is in the conductor where E bar is equal to 0. Where E bar is equal to 0 minus. So C to B to C, because B to 2 is in the dielectric, C to 2 to C is in the conductor, the second term becomes a 0 here. See, the second term is a 0. Delta H by 2 only. Got it? So integral B to C, the DL bar is a delta H by 2. And E is in the normal component because it's a parallel to the of En. Okay. And second integral, first integral becomes E tan delta omega. And second integral, only we can take the which part is there in the dielectric. The another part in the conductor is a 0. So that is En into delta H by 2. Okay. And now the third integral. See, delta omega is in the positive direction and it is the, let us take this is a positive integral. Definitely the direction is a reverse direction. So if you can take it is a negative and the D2A is in the positive. If D2A is in the positive means B2C is in the negative. Okay. Here they take En into delta H by 2, the B2C. The B2C is a positive value means similarly the path D2A. The condition is same for the both the BC and BC, only the direction is opposite direction. So D2A E bar dot DL bar is equal to minus En into delta H by 2. So only the direction is different. It is outward downwards and it is upwards. And third integral now it becomes of En into minus En into delta H by 2. Total integral is equal to 0 minus 2. So now En delta H by 2 minus En delta H by 2 both get cancelled. So E tan delta omega is equal to 0. In this, delta omega is not at all equal to the 0. Not at all equal to the 0. Then to get this equation as a 0 means E tan is equal to 0. E tan is equal to 0. This is the first condition. And similarly, the D tan is equal to, what is the relation between of E and the D is mu into, not mu, sorry. Mu into E tan. When I'm taking the D tan, it's a mu tan. Again, I wrote that is a mu only, sorry. It is epsilon minus 2. Epsilon into. So E tan is a 0, means the D tan is also the 0. Substituting the E tan is equal to 0, D tan is also 0. So the tangential component, the boundary between dielectric and the conductor, E tan and the D tan is both are the zeros. Okay. So here, so finally, the substituting the 4 and the 8 equations, 9 equation in the 3, we get E tan delta omega plus E n delta h by 2 minus E n delta h by 2 is equal to 0. E tan delta omega is equal to 0, but delta omega is not at all equal to the 0. As a finite, we have to get E tan is equal to 0. Thus, the tangential component of electric field intensity is a 0 at the boundary between conductor and the free space. Conductor and the free space. Okay. And the relation, we know that d bar is equal to epsilon into E bar for the free space. D tan is equal to epsilon into E tan, that is also the 0. Thus, the tangential component of electric flux density is a 0 at the boundary between conductor and the free space. Okay, both the tangential component and tangential component of electric field and the tangential component of electric flux density both are zeros. Now we go for the normal component. To find the normal component, D bar is selected as a closed Gaussian surface in the form of right circular cylinder. See in the diagram, the two diagrams are there in the boundary between dielectric and the conductor. Rectangle, I took that as a rectangle to find the tangential components. Now I take the cylinder to find the normal components of electric field and the electric flux. The height of that cylinder is a delta H and the surface is a delta S. And there is a Gaussian surface inside. Half part is there in the conductor and half part is in the dielectric or the free space. Now, according to the Gauss law, Q bar is equal to D bar dot ds bar integral. According to the Gauss law, integral D bar dot ds bar is equal to Q. The surface integral must be evaluated over the three surfaces because we assume a cylinder to find the normal component. To find the normal component, the boundary between dielectric and the conductor. Half part is in the dielectric and half part is in the conductor. Okay, here the delta x surface and height is a delta h. Okay. Now there is a top is there and the lateral side and the bottom. Okay, bottom is in the conductor and top is in the dielectric. We know in the conductor D is a 0 and E is also 0 and the charge density rho v is also the 0 minus. So the bottom part, whatever we have, we can take here. The surface integral must be evaluated over the three surfaces. One is a top and one is a bottom and the lateral side. And integral d bar dot ds bar is a top, integral bottom d bar dot ds bar plus integral lateral side, the d bar dot ds bar is equal to q. according to the gas law. Okay. So bottom is in the present in the conductor means the second integral is equal to 0. The bottom surface is in the conductor where d bar is equal to 0. Hence, the corresponding integral is a 0. The remaining the two integrals. One integral is integral d bar dot ds bar of top and integral lateral side of d bar dot ds bar is equal to q. The top surface is in the free space and we are interested in the boundary condition. Hence, the top surface can be shifted at the boundary with the delta h tends to the 0. Delta h tends to the 0. Means the lateral side is also becomes a 0 minus 2. The lateral surface area is a 2 pi r into delta h, where r is the radius of the cylinder. But as the delta h tends to 0, this area reduces to the 0 and corresponding integral is also the 0. So lateral side is also 0. Got it, my students? Now the remaining only the top, while only the component d bar present in the normal component having the magnitude dn, the top surface is very small over which dn can be assumed the constant and can be taken out the integration. That is integral top d bar dot ds bar is equal to dn into the integral top of ds bar. What is the integral ds bar is nothing but delta s. Okay, the total surface, incremental surface. Previously we took the E integral dl bar is equal to delta omega, the width of that rectangle. Now here the cylinder is there. The integral of surface integral ds is equal to s actually. S is a small incremental surface, that is a delta s. We are finding the normal component, so take the t bar as a dn into delta s. Okay, and it is equal to the q. dn is delta s is equal to the q. Got it, my dear students? And then q is equal to, we know the q, dq by the ds is equal to rho s. And dq is equal to rho s into ds. And q is equal to integral rho s into ds. And that is equal to rho s into integral ds. What is that integral ds? Again, we represent that integral ds is the delta s. So q is equal to rho s into incremental surface delta s. So finally, the integral d bar dot ds bar of the top, because it is in the dielectric, it is not the 0. Lateral side is a 0 when delta h tends to 0, and bottom side is also 0 because it is in the conductor, and the topmost is not the 0 and is equal to the q. What is the q we have? Q is equal to rho a, okay, q, and integral d bar dot ds bar we got dn delta s, and the q is equal to rho s into delta s. Q is equal to rho s into delta s. So delta s get cancelled. dn is equal to rho s. dn is equal to rho s. Thus, the flux leaves the surface normally, and the normal component of flux density is equal to the normal component of flux density is equal to rho s is equal to the surface charge density rho s. And what about the En? The relation is there. The dn is equal to epsilon naught into En. So En is equal to dn by epsilon naught. What is the dn? The rho s by epsilon. So En is equal to rho s by epsilon. Got it, my students? So here we got the boundary conditions, the tangential component E tan is equal to 0. The surfaces of the conductor is an equipotential surface. The potential difference along any path on the surface of the conductor E bar dot dl bar as E bar is equal to E tan, that is equal to 0. Finally, the boundary between the two conditions, between a conductor and the dielectric, E tan is equal to D tan, that is equal to 0. And the normal component dn is equal to rho s, En is equal to rho s by epsilon, that is not the epsilon naught r. In the free space, epsilon r is equal to 1. Okay. In the free space, the dielectric epsilon is equal to epsilon naught. Thus, the boundary in between the conductor and the dielectric, E tan and the D tan is both are the zeros, means tangential components of electric and the electric flux both are the zeros. And normal components of electric and the electric flux is the rho s, electric field is the rho s by epsilon. Okay. It's a very, very important matter. So boundary conditions between conductor and the dielectric. The second one is the boundary conditions between the two perfect dielectrics. Two perfect dielectrics means the boundary is between the conductor. Instead of conductor, here you can take the below the dielectric and above is also the dielectric. Only the E bar and D bar is the zero in conductor, not the dielectric. So again, to find the tangential components, assume the rectangle with the width of delta omega. Half part is in the dielectric 1 and half part is in the dielectric 2. In the dielectric 1, assume that is epsilon 1. In the dielectric 2, epsilon 2. And height is also half part is in the dielectric 1 and half part is in the dielectric 2. AB, C, D. AB is in one direction, DCD is in another direction, opposite direction, BC is in one direction, and DA is in the opposite direction. Okay. Here is a E tan 1, because in the dielectric 1, to find the tangential component is E tan 1. In the dielectric 2, E tan 2. Okay, my dear students. Now again, integral E bar dot dl bar is equal to, got it? Both are B to A to B. The four integrals, that is A to B, E bar dot dl bar plus, and the B to C, E bar dot dl bar plus C to D, E bar dot dl bar plus D to A, E bar dot dl bar is equal to 0. Okay, my dear students. Now, E1 is equal to the combination of the tangential and the normal component is E tan 1 tan and the E1 normal. This is E1 tangential component plus E1 of the normal component. Okay, my dear students. The next is E2 is there. E2, the combination of the tangential and the normal components. E2 is equal to, because we are considering the boundaries between the dielectric and the dielectric only. Got it? Like this, there's a boundary line is there. Dark shaded line is dielectric 1 and light shaded line is the region 2, nothing but dielectric 2. Okay. Now, the tangential components E tan 1 and E tan 2 and the normal components E1n and E2n. There is a two dielectrics means you can name it as a tangential 1 is the dielectric 1, tangential 2 in the dielectric 2. In the previous case, there is no any two dielectrics. One is a dielectric, another one is a conductor. Okay. See, now for the rectangle to be reduced at the surface, it analyze the boundary conditions. Definitely can take the lateral side is a 0. Delta H tends to 0 as integral B to C and the D to A becomes a 0. Becomes a 0 because B to C is in one direction and D to A is in the other direction, and delta H tends to 0. The two integrals are the zeros. Okay. What is the two integrals here? One it is a B to C. Another integral is a C to D. And remaining, we have the two integrals A to B and D to E. A to B integral E bar dot DL bar and C to D integral E bar dot DL bar. Okay. The lateral side only we have the zeros. Okay. And A to B is in the dielectric 1 and C to D is in the dielectric 2. Okay. See here. A to D with the width of delta omega is on dielectric 1 and C to D is in the dielectric 2. So now the integral A to B E bar dot DL bar is a E tan 1 into delta omega, and opposite direction C to D E bar dot DL bar is minus E tan 2 delta omega. Okay, substitute these two equations. E tan 1 delta omega minus, because the one is A to B and one is C to D. Both it is a delta omega, it's a width only, but direction is a difference. So first one I am taking the E tan 1 because it is in the dielectric 1, and second one is a E tan 2 because it is in the dielectric 2, and both the width is delta omega, but the sign is depends upon the sign is the direction of. Okay, is equal to 0. Now E tan 1 is equal to E tan 2. Delta omega and delta omega get cancelled. E tan 1 is equal to E tan. And coming to the is electric field and electric flux relation of E tan 1 and the E tan 2. D tan 1 is equal to epsilon 1. I am taking the E epsilon 1 into E tan. Got it? And D tan 2 is equal to epsilon 2 into E tan 2. What is the E tan 1 from this? E tan 1 is equal to D tan 1 by epsilon 1. From this equation, E tan 2 is equal to D tan 2 by epsilon 2. Now we got the E tan 1 is equal to E tan 2. Compare, equate these two functions. D tan 1 by epsilon 1 is equal to D tan 2 by epsilon 2. Or otherwise, the ratio between of tan D tan 1 by the D tan 2 is equal to D tan 1. The cross multiply here, we get the epsilon 1 by epsilon. Epsilon 1 by the epsilon 2. D tan 1 by the D tan 2 is equal to epsilon 1 by epsilon 2, and E tan 1 is equal to E tan. Got it, my dear students? So see here, the E tan 1 is equal to E tan 2. E tan 1 is equal to E tan 2. Thus, the tangential components of the field intensity at a boundary in both the dielectrics remains the same. That is, electric field intensity is a continuous across the boundary. Remember this, my dear students. Since these two are equal, then the tangential components, electric field intensity is continuous across the boundary. Okay. And what is the D tan 1 and the D tan 2? The ratio between of tan D tan 1 and D tan 2 is the epsilon 1 by the epsilon. Thus, the tangential components of D bar undergoes some change occurs, the interference, hence the tangential D bar is said to be discontinuous. When both are equal, it is a continuous. The tangential component of D bar undergoes some change occurs in the interference. Hence, the tangential D bar is said to be discontinuous across the boundary. Okay. And coming to the find out the normal components, you can go for taking the Gauss law. Again, top and the bottom and lateral. Lateral is always a 0, with delta H tends to the 0. So D bar dot ds bar is equal to, actually it is a Q. To find the normal component, let the Gauss law consider a Gaussian surface in the form of a right circular cylinder placed in such a way that half of its lie in the dielectric 1. Okay, half of just it is a boundary. And if I am taking the one cylinder, half part is in the dielectric 1 and half part is in the dielectric 2. So the lateral side, the delta H tends to the 0. The lateral integral becomes a 0. Thus the surface area of the top of the bottom is delta S. So integral d bar dot ds bar is equal to Q. 3 integral d bar dot ds bar is equal to Q. Okay. Now, but the lateral side, the d bar dot ds bar is equal to 0 as delta H tends to the 0. And top and the bottom is equal to Q. What is the top? D1. Okay, integral d bar dot ds bar as a top dn1 integral ds bar it is. Okay. And bottom one, the integral d bar dot ds bar, because it is in the dielectric 2, dn2 integral ds bar. Add the two functions and is equal to the q. What is here? The dn into delta s only, a small incremental value. So dn1 into delta s. Okay. For the top surface, the direction of dn is entering the boundary, while for the bottom surface, the direction of the dn is leaving. So both are opposite direction at the boundary. So the minus dn2 delta s is equal to q. So what is the q we have? Delta n1 into delta s minus delta n2 delta s is equal to rho s into delta s. So common term is the delta s get cancelled. So dn1 minus dn2 is equal to rho s. Because both are in opposite in direction at the boundary. You take the negative sign in between. So dn1 into delta s minus dn2 delta s is equal to rho s. So dn1 minus dn2 is equal to rho s. There is no free space, free charge available in the perfect dielectric. Hence, no free charge can exist on the surface. All the charges in the dielectric are bound charges and are not free. Hence, at the ideal dielectric media boundary, the surface charge density rho s can be assumed as a 0. Since why it is a 0 means there is no existing of the charges because both are is a dielectric. Both are is a dielectric. In the previous case, there is a bottom, we have the conductor. Inside there is no any surface charge density or the charge density. There is on the surface there is a surface charge density is there. But here the both are in the dielectric. Assume the rho s is so dn1 is equal to dn. So this one is a continuous now. Previously, the tangential components is both are continuous. Now here the normal components Gn1 and Gn2 are the continuous. Hence the normal component of flux density d bar is continuous at the boundary between the perfect dielectrics. Now the relation between flux density and the field intensity is epsilon 1 into En1 is equal to epsilon 2 En. So the ratio between of En1 minus not the minus by the En2 is equal to En2 is epsilon 2 by the epsilon 1. Okay. Now the normal component of electric field intensity E bar is discontinuous at the boundary between the dielectric and the dielectric. Okay, my dear students. So we got En1 by the En2 is equal to epsilon 2 by the epsilon 1. The normal component of the electric field intensity are inversely proportional to the relative permittivities of the two medium, and it is a discontinuous because both are equal. We can call it as a discontinuous, and En1 by the En2 is not equal and is having the some value the epsilon to the epsilon 1, then it is a discontinuous, the normal component. Understood, my students? Okay. So we find, finally we conclude that the boundary between the conductor and the dielectric, the first case, E tan and D tan both are zeros. E tan and the D tan is both are the zeros. Okay. And the second case in the dielectric, E tan 1 is equal to E tan 2. And the D tan 1 by epsilon 1 is equal to D tan 2 by epsilon 2. Okay, these are the tangential components of the conductor and the dielectric between. And here this is the dielectric 1 and the dielectric 2. But in the normal components here, the both are equal. For the second one, the normal components are dn1 is equal to dn, as is of tangential components. And E tan 1 and the E tan 2. So En1 by the En2 is equal to epsilon 2 by the epsilon. Epsilon 1 by the epsilon. This is a dielectric. Both the boundary conditions are the dielectric and the dielectric. Got it, my dear students? So these are very, very important. The boundary surfaces between the conductor and the dielectric, and between the dielectric and dielectric. Okay, my dear students.